the workshop. And I think Nisheeth is definitely a very long-term friend of Simon's, and he has visited Simon's many times already. And today he's going to give a virtual talk on computationally efficient alternatives to min-max optimization. So without further ado, yeah, Nisheeth, the stage is all yours. Yeah.
Thank you so much for the invitation and the introduction. While I'm delighted to give this talk, I must also say that what is happening in the world is very tragic, and perhaps give some more motivation for us to think about various things in life besides research, but maybe think more carefully about adversaries, which is what this talk is going to be about. So the message of this talk is actually very simple. We are going to explore min-max optimization problems, which are used to model many situations in machine learning, economics, theoretical computer science, game theory, to model learning or decision-making in the presence of adversaries. It's a very important problem. However, unlike its relatives, minimization, there has been some issues related to try to find out what should be a notion of a solution here. And in this talk, I will propose a notion which is called greedy adversarial equilibrium, which is something that we came up with Oren Mangubi in a paper in 2021. And it is a restriction on the max player. And what it does is allows us to define or new notions of equilibrium, which we then show exist under less strict conditions and also can be found efficiently. Okay, so let's start this talk from the connection between learning and minimization. I guess everybody here would be bored in the first few minutes of the talk, but let me just do that anyways, in case there is someone who's not quite sure where I'm coming from. So one of the key successes in the last few decades has been reducing many machine learning tasks to optimization or minimization, where the functions that we want to minimize encode the data from which we want to learn from. And with the availability of really large scale real world data sets, along with our ability to do non-trivial computations, we have made a lot of success. We have achieved a lot of success in this area. I guess we have been looking at, historically, the machine learning community has been looking at non-trivial functions which can encode the loss, giving rise to various non-convex objectives, which are in general NP hard to optimize. However, there are many efficient notions of local minimization which exist for non-convex optimization. And let me mention one of them, which is actually relevant to this talk. This is the notion of epsilon local minima, presented by Nesterov and Polyak in 2006. So for a given function f, which is not necessarily convex anymore, we say that a point x star is a second order epsilon local minimum if it satisfies the following two properties. One is that its gradient at the point x star is small, less than epsilon, mimicking or trying to mimic the fact that if it's zero, then it's a stationary point. And the second is that its Hessian at this point x star is not too small, or the eigenvalues of the Hessian are not too small. In particular, all eigenvalues of the Hessian are at least minus square root epsilon. So this relation between epsilon and square root epsilon is not quite clear from this definition, but it is important for their definition, something that I would be unable to explain in this talk. But let's just think of this definition. If it's helpful, you can also introduce two different parameters here, epsilon and delta. So the key point which this definition seems to be useful for is that at any point which is not an epsilon local minimum in this sense, one can decrease the value of the function by epsilon in taking about poly 1 over epsilon steps. So the key number to focus here is on 1 over epsilon, and things like L and logarithm in the dimension is also important. So L is the Lipschitz constant of the function. And yeah, but there's no assumption on convexity here. So using this, using this idea, Nesterov and Polyak gave an algorithm which runs in polynomial in 1 over epsilon L and log D. And subsequently, there have been improvements by various groups of people, some of them in Berkeley, and probably present in the Simon semester that's happening right now. So the story of local minima in the case of minimization has had a good run. So we're going to switch and try to see what happens when we want to do something more than just learning from data. Data that we're learning from may not be accurate, or our assumptions about the data might not be accurate, in which case the question would be how to model the data. And so what are the possibilities? Well, one is that the data could be noisy. And the second is that the data could be adversarially perturbed. Now, these are, of course, two of the many possibilities that you can imagine. But the question that arises is, how does the learner continue to learn from such data under the presence of such perturbative channels? And these adversaries arise, of course, in simple, just the basic machine learning problems, but also in other problems such as privacy, where there may be a where the data might be perturbed on purpose to protect the privacy of the individual, or the data might have systemic biases which are encoded and whose nature might not be known. So min-max optimization has been used as one of the solution concepts to do learning in this setting. And the traditional framework considers functions, so it will model the learning problem in the presence of an adversary by two sets of variables and a function. One set of variables, x, is the set of variables or the model parameters that belong to the original learning problem. And one set of variables, y, typically belongs to the adversaries who can either perturb the data or do something else. And this gives rise to functions f of xy, which depend both on x variables and y variables. The goal of the x player is to minimize the function f, and the goal of the y player is to maximize it. So this is, and there is a sequence here. So min, max, this is, it's not the same as max min. So in this setting, I would say the case of convex-concave functions f is somewhat better studied, and there are a lot of works. But in many machine learning applications that we would like to use this, f is non-convex in x and non-concave in y. So while this model is really great, it is very flexible and very powerful, it's not clear whether we can define even locally convergent algorithms for these these models. Yeah, I guess one should keep in mind that, at the end, at least from where I come from, I mean, the goal is to solve the original learning problem in the presence of adversaries, and min-max optimization is one particular way to do it. So, and I guess this is where this talk is going to be heading, that we are going to be focusing more on this and be willing to relax this notion of min-max optimization to something different, which we're going to talk about. So I guess here in the audience, everybody has hopefully seen the example of GANs, these generative adversarial networks, which have been used for a variety of tasks, and are kind of the quintessential introduction to min-max optimization to a machine learning community, because the way they were formulated, it is in the min-max setting, although there are variants of it as well. I don't want to talk too much about GANs, given that this is a 40-minute or so talk. But in case you wanted to see a practical example, this is one motivating example from unsupervised learning. So let's talk a little bit about local equilibrium for min-max optimization problems. There have been many prior attempts to define a notion of an epsilon local min-max point. And roughly, several of them try to say a point, x star, y star is epsilon local min-max if y star is some kind of a local maximum of f for a fixed x star, and x star is an epsilon local minimum for f for a given fixed y star. So this is, in this sense, it's actually a true equilibrium and something really satisfying in the sense that if we fix y star, if we fix x star and the max player can only use local algorithms to improve their payoffs, this definition makes sense, and same for the min player. However, there are many even simple examples and complexity reasons why this may be a tricky notion to make computationally efficient. For one, such points may not exist, and there are examples, in particular in paper by Jane Netrapalli and Jordan. And even under the presence of, even when one can show that they exist through some existential results, they may be computationally hard to find, as was shown in a paper by Daskalakis, Skoulakis, and Zempatakis in 2021. While I don't have time to go into the details of why these things don't exist, one of the issues seems to be that learning agents who can only make local predictions, so these notions of local maximum and minimum are what I'm referring to here, are generally unable to predict their opponent's responses. And this leads to a convergence problem in many algorithms, such as gradient descent ascent. As this GIF on my title slide was showing, so there is this issue of non-convergence. It can spiral out and may cycle and various other behavior. So a big body of work has focused on identifying conditions under which they can guarantee and find local min-max points. Yeah, so this is a list. It's not at all comprehensive, so apologies if I missed out your paper. I know there is a huge and rapidly growing body of work in this area. Some of the assumptions include that the function is bilinear, as was made by Daskalakis and Panagias, or we have access to some specific and special starting points, as was the case in the paper of Heusel, Remauser, Untertheiner, Nestler, Hochreiter in 2017, or that the function is concave in one variable, for instance. Yeah, so there have been there's been really a lot of work. So why, okay, so these are, one can argue that these are theoretical issues, whether actually there is a problem in the real applications. And the answer is yes, there is a problem. It's not just a matter of, so this is one of the problems in machine learning, where it's not just a matter of using theory to explain something, but actually using theory to come up with and go beyond the issues that currently exist, which even non-theoreticians are somewhat unable to answer or address. So I guess in terms of GANs, and I'm not sure how popular GANs are these days, but GANs, have shown to have cyclic behavior. So for example, this is a simple case where there are 4 Gaussians centered at these red points with very small variance. And you can see that when we use something like gradient descent ascent, it learns a mode, but then it forgets it and goes to another mode, and so on. So it starts showing this cycling behavior. And there are other issues such as this non-convergence or instability that has also been observed with these simple algorithms. Okay, so now coming to this talk, the key idea, which I mentioned in the beginning of the talk, is to change the model from min-max optimization to something where the max player is a bit more restricted. So the max player will be computationally restricted. The max player, remember, is the adversary. And what we do is to, in a nutshell, say that the adversary will only move to a new point if it can see a path from the current point to a new point, which is increasing its objective function by at least some amount. Okay, so this is the conceptual, this is really the key takeaway from this talk. Now, why would this make sense? Well, this doesn't make sense, first of all, in every situation where the adversary can, if one is trying to model a very powerful adversary which can jump from a point to another point, having access to magic computational powers, this notion will not insure you against that. But if the adversary is using algorithms themselves, and in particular greedy algorithms, such as SGD or gradient descent and so on, we will see that it can potentially guard us against such adversaries. And the main theorem, which was obtained in a joint work with Oren Mangubi in 2021, is that if you're given access to a function f and to its gradient and Hessian, we can, from any initial point, find an epsilon greedy adversarial equilibrium, which is going to be defined in the next slide, in time, which depends polynomially on d, 1 over epsilon. So d is the dimension, 1 over epsilon is the error, and b and l are some constants associated to the function f. It doesn't make any assumptions on the starting point, concavity, coherence, bilinearity, and so on. We show that such an equilibrium actually exists for every bounded function with Lipschitz Hessian. And if you're wondering what the connection of this equilibrium is, to the to the case of convex concave gains or convex concave functions, we show that the epsilon greedy equilibrium that our algorithm will find is also an epsilon global min-max point in a technical sense. So so I don't know what the plan for questions is, but if you have anything that comes up, just feel free to interrupt me. But I can also take a 20-second break here to see if anybody has any questions before I go on to talk. The talk is going to become a bit more technical.
I had a question.
Yeah. Hi.
Hi, Yelena. Hi, Nisheeth. So I was just wondering about this assumption that F is uniformly bounded by some B, because this wouldn't already hold, like for some examples even of convex concave problems. So can you comment a little bit more on that? Can we just take this to hold in a neighborhood and then it is sufficient, or how would you?
So this is an important assumption, and you are right that this doesn't always hold. So the way we can deal with it in the case where this doesn't hold is to have some bound on where the solution lies, where the global min-max solution lies. Suppose we have some idea of a bounding box for this, and then we can restrict our function to this bounding box. And that then will give us a bound on how big the function can be.
I see. So if I'm understanding correctly, essentially, if you initialize close enough to a solution and your function doesn't do anything crazy, and it wouldn't because it is.
That's right. Yeah.
Lipschitz,
I mean, this is also, for example, if you do gradient descent and then you have to prove a convergence bound, I guess there is some dependence on the distance between the starting point and the optimal point and the number of iterations, right? So
that makes sense.
So I'm not saying it is the same, but it's an important assumption in the theorem, and at least in all interesting cases, this seems to be obtained through an auxiliary analysis. Yeah. Thank you for the question. Excellent question. Okay, so I will move on and talk about greedy paths and our definition of equilibrium. So the idea of greedy path is really just what the word greedy path say. So you are at some point, let's say x comma y, and so let's say you are the min player and you are trying to understand what the y player can do. So here is the set of strategies you allow the max or the y player to use. And of course, none of this will work if the y player is more powerful than this. But let me just say what the strategy space is. So the strategy space is that y player can go from y to w, which is another point in the space, as long as there is some path from, as a continuous path from, the y to w, where the derivative of the function is increasing and the second derivative of the function is also increasing. And this epsilon root epsilon is motivated by the Nesterov-Polyak definition. For this talk, you can just assume that this is positive. Both these numbers are positive. But yeah, if you want to get quantitative bound, just positivity is not enough, and we need these numbers to grow in a specific at a specific rate. So you can also just think of, if you want to model first order algorithms, then you can drop the second condition and just require that the value of the rate of change of the value of the function across this path is large enough, more than epsilon, And you can see that this does, this notion of greedy path models, some classes of first and second order optimization algorithms. And so, it is restrictive. It is more restrictive than the general min-max setting. But it might be useful to consider if you are not dealing with an all-powerful adversary, but something which itself has access to algorithms, an efficient algorithm. I mean, after all, how will this adversary, what will this adversary use to de-equilibrate the situation for the Y player, also for the X player, for the min player? So this gives rise, this definition gives rise to a notion of, a new function, which is what we call the G function. So the G function at a point xy is the maximum value of f, where x is the same as the input to x, but the maximum is taken over all paths starting from y, which are reachable from y via greedy paths. Okay, so all g which are reachable from y via greedy paths. So now if I look at this picture here for illustration, suppose you are at this point A. So the point B seems to be reachable by a greedy path because you're always only increasing. There may be non-greedy paths to reach here as well, but there is at least one greedy path to reach here. But this point C, which is in this picture, the true maximum, doesn't seem reachable. So the adversary, if it wants to go from A to C, will have to incur some significant losses before it actually starts gaining. Note that one of the key differences between this this notion and things like GDA is that we are not restricting how many steps the adversary can take. And this becomes very important. So maybe the instability or the cyclic behavior was because we were limiting we were limiting in some sense the adversary there as well by saying the adversary can only look ahead so much. So maybe there was a limit on some kind of a memory of the adversary, or but here we are not restricting that. We are assuming the adversary to be greedy. And I think these kinds of models, and I'm sure there will be others, might be interesting way to think about the problem where there is some context, and in that context, min-max might be too strong. Okay, so as a first attempt, we can define now an equilibrium for our framework by extending the definition of Nesterov and Polyak. It's in a pretty straightforward manner. So we have two functions. One is the gradient of f with respect to y, and one is the gradient of f with respect to x. But we replace f with this greedy max function. And we say that point x star y star is an epsilon greedy equilibrium if we look to y and the Hessian of f with respect to y, they are small. While at the same time, the derivative of g with respect to x and the Hessian of g with respect to x behave in this manner. So even though Nesterov-Polyak defined only for minimization, I mean, clearly it implies a similar local maximum definition, which is what we are using here. Okay, so what is the problem with this? Well, there is a slight problem. This definition, which involves taking a supremum over all paths reachable from y, even though greedy paths, this function can be actually discontinuous. And this is not just some side case, but this can actually happen. So we need one get around, and what we do is we basically smoothen the function. So without going into a lot of technical details, but if a function is not really continuous, one can smoothen it out by averaging it around the point by doing a short random walk around that point and just associating that value. So that's what this function s does. It is some smoothing of this function g in the x variables. And there's also some technical reasons for us to truncate the function, but let's not get into so many details. But this is really it. I mean, this is the idea. So if for whatever reason the function g ended up being smooth itself, continuous itself, then this is the definition. So once again, so what did we do? We restricted the max player or the y player to just greedy paths, epsilon greedy paths, second order epsilon greedy paths in this setting. And we used the definition of Nesterov and Polyak. We just plugged it in one case for the function f, because we are not really restricting the min player. So that's, it is what it is. But since we are restricting the y player, we need to change the function with respect to which we are applying this definition of Nesterov and Polyak. So any questions about this definition?
There was a question in chat by Emmanuel, like he was asking, like in the initial paper, smoothing is using like a randomized Gaussian convolution, and do you see a way to de-randomize the smoothing?
Oh, that's a great question, and so in practice and in our, in this other paper that I will mention at the end, what we do is to actually, maybe I'll answer this question in a little bit more detail once I introduce that. But yes, there are possibilities to do that. We don't want to add a Gaussian in general. So Gaussian is nice to obtain theoretical results, but the issue with the Gaussian is that it leads to a polynomial in D dependence in the running time. And that, while in theory it is fine, in practice, since most of optimization is dimension independent or depends logarithmically on the dimension, that's not necessarily a great thing to do. So we must use somehow the geometry of the problem when we are choosing this. And there may be some ways in which one can potentially try to de-randomize, although currently we don't know. But you could imagine that you could certainly reduce the randomness by looking at the, for example, if this was, instead of looking at the covariance matrix, which is just identity, you could look at a covariance matrix, which is obtained from taking the Hessian of the function at the point you are, or some lower dimensional version of the Hessian. So in practice, you can do all kinds of fun things to obtain the same effect, but it's not, it's not clear to me that randomization is absolutely necessary. So I'm sorry, I don't have a very satisfactory answer to your question, but this is a great direction to think about. Okay, so how to minimize this function? So that's okay. All this sounds great. What are we going to do with this? So yeah, I think maybe you want to see why, get some feeling of why it may be discontinuous as well. For example, if you start from this point here, xy, take a greedy path, you might reach here, which is this side of the ridge. Whereas from a close by point, you might reach actually a completely different side of the ridge. So discontinuity comes in the sense that when we perturb this point, we can fall here or there, anywhere. Yeah, so this is, I mean, even the landscape is very smooth here. So it's not the issue of the landscape, actually, it's the issue of the definition. but this definition is robust for convex-concave function. Function is convex or concave, there is no problem. It's a natural definition, and that is why we can kind of relate to the results in the convex-concave setting. So yeah, how much time do I have? I just want to plan the talk accordingly.
I think you can still take 5-6 more minutes because we actually 10 minutes because we started a bit late.
Okay, yeah, okay, I'll try to wrap up in 10 minutes. Thank you. Yeah, so you know, you know, forget the case of smoothness, I mean, or differentiability. Even when G is differentiable, the way the function G is defined, it's a supremum over these infinitely many paths. So how do we minimize this? How do we have access to gradient or anything? So here we use an idea which goes back to a very nice paper by Flaxman, Kalai, and McMahon from 2014, which allows us to get estimates, unbiased estimates of the gradient of a function by zeroth order access to it. So what we can do is to compute, you know, well, let's see, I'll talk about it in the next slide, but let's assume for a moment we can evaluate this function G. So then this trick of Flaxman, Kalai, and McMahon allows us to compute the gradient. But now you may ask, you know, why can we assume, yeah, so you can kind of, yeah, and once you have access to this, you know, gradient, you can run stochastic gradient descent. The only thing we do is to add noise. This is to incorporate the smoothing step in a stochastic manner. And we can show that noisy SGD returns an epsilon local minimum of this function for any given y hat in poly in D, L, B, and 1 over epsilon steps. Okay, so what does the algorithm look like? The algorithm is iterative. There is some point x hat, y hat. And what it does is it keeps moving from points xi, y hat to some new point. And so that's really what happens. There's an input point x hat, y hat, and there's an output point xy. So roughly speaking, it starting at x hat first makes a move for the min player. So the min player update its strategy based on its estimate of this greedy max function, the noisy greedy max function. So that's what is happening here. So the X player or the min player is updating its strategy based on its understanding of what the greedy adversary can do with some noise. And it accepts that direction if it sees a significant decrement in its value. So the min player is trying to minimize. So it should not accept every move. It should accept moves which are reducing its objective value. And in this case, we want the reduction to be significant in the sense that it's at least poly 1 over D and epsilon. And then once X is updated, the Y player will run the second order maximization algorithm starting at Y hat to compute this new point. And this gives us a new point. So this does leave this issue of how to compute G. And that's something I'm going to talk in the next slide. And that will be the last technical slide, I think, in the talk. But the proof is not too difficult. In fact, it's kind of the algorithm very carefully has things which enable the proof. So roughly speaking, I mean, G decreases by some non-trivial amount, Pauline 1 over D epsilon amount at each iteration. And so if the function is bounded, the algorithm converges in this many iterations. And that's where we need, very crucially, an upper bound on the value of the function. If there was no upper bound, then we can't say anything. But if we know, for example, what is some target upper bound, and we have some region where we can kind of auxiliary guarantee it, we would be fine. If you reach a point where the X player is unable to decrease the function G, then we can conclude that we reached a greedy max for us. So this X star for this smooth version of the greedy max at this point Y star. And we can show that the point X star Y star where our algorithm stops is this epsilon greedy max that we were looking for. So in particular, it's epsilon local min for the smooth G function and an epsilon local greedy max for the function F. So one last obstacle which I want to discuss is computing G. G as defined is a supremum over all possible paths from X, Y. Even though these paths only traverse the Y dimension, they are allowed to travel as long as the value on this path is for Y is increasing. And this creates this very, very huge and infinite search space. It's not clear how to handle that. And in general, finding the maximum of all these paths is certainly intractable. So what we do is, again, simplify G to some lower bound on G, which we call this function H, which is obtained by just sampling one greedy path. So out of all the greedy paths that you could take from X, Y, all the Y greedy paths that you could take from X, Y, just sample one. And we show that this function or this lower bound actually turns out to be enough for us. The details are not too difficult, but I think given I have 2 minutes, I want to skip these details. But these are all the ideas. I mean, I wanted to focus on the ideas in the talk, maybe giving some sense of what technically is going on. I hope you got this so far. So now coming to the first order algorithm, with Vijay Keswani or Mangubi and Sushant Sachdeva, we actually considered a first order notion, which is a simplification of what we considered in this paper, where we would only consider, we will not consider the Nesterov-Polyak equilibrium condition, but the first order condition, which means that we only restrict the gradient to be small, but we still restrict the Y player to be only a greedy player. Okay, so it can only move along paths. And we can show that in this setting, we can get an algorithm which is logarithmically dependent on the dimension. Although the notion of equilibrium is not as robust as the one that we presented in this talk. But this is a paper which has a real practical motivation. So it's very fast. Its running time in the end is something comparable to GDA. So we could compare our algorithm to things like GDA. And we observed that our algorithm avoids cycling and consistently shows improved multimodal learning. These are some, I mean, this paper with Keswani, Mangubi, and Sachdeva has lots of more simulations on synthetic and real world data sets in case you want to look at. But some of these pictures which I mentioned where GDA seems to fail is our algorithm seems to be learning multiple modes. So yeah, I mean, this does lead to something useful in practice. Okay, so I'll conclude. The the main contribution of this work is to consider a restricted adversary in the min-max optimization framework, a computationally restrictive adversary. And this leads to a polynomial time convergent algorithm for such for certain bounded and Lipschitz functions without any other assumptions on the starting point, concavity, and so on. The notion does naturally generalize the setting of convex-concave, which has been very well studied. The first order algorithm has a weaker notion of equilibrium, but a faster notion of faster running time. And it also contains applications to training GANs. And I guess one of the main open problems that remains, direct open problem that remains is, can the second order greedy adversarial equilibrium be also found in polylog D gradient evaluations? So the Nesterov-Polyak result depended polylogarithmically on D, whereas our work depends polynomially on D. And the key obstacle to this is this Gaussian smoothing step. Yeah, so this is all I have to say. Thank you so much for your time and attention. And I'm happy to take questions.
All right, thanks so much for the very interesting talk. I don't think you'll hear our applause, but yeah. Right, I personally find it's very interesting for this notion of adversarial equilibrium and also this first order greedy path, because I think in practice, like a lot of those adversarial attacks are based on this first order dynamics. So this is for sure very interesting. So I think Mannoy has another follow-up question about the unbounded domain, as Inina pointed out earlier. Like he was curious that whether this would extend to, whether this would be robust to other like box constraint optimization, etc. Yeah.
Yeah, so that's so one can restrict the adversary to, so another way to deal with this is to restrict the adversary to making updates to greedy paths, but limiting how far they can go. And such notions have been considered, that where you would have a ball around this point, the current point, and you would say you can go from here to anywhere in this ball. So that's another way to bring in this boundedness in some way, I would say. But that notion, I mean, the difference is that so what we do, we assume that the function is bounded, but the Y player can go as far as it likes, and still there will be a point where things can converge. Just having a ball assumption on the Y player and the X player, which is what many local min-max algorithms, optimization frameworks try to do, still doesn't guarantee the existence of a convergent, at least to the best of my knowledge.
I see. Thank you. Yeah. Are there any questions from the audience?
Yeah, hi, Jelena.
Yeah, I just had another question. So it's just related to the guarantee you mentioned when you use this Gaussian smoothing, right? So the guarantee for the min part, if I followed correctly, is with respect to the smoothed version of the function. And is it actually possible to also say something about the guarantee with respect to the original function? I mean, my sense is that, if your function doesn't look too crazy and you're using kind of sufficiently small amount of smoothing, you're not going to erase the local behavior.
Okay, so let me just first try to make sure that I understood your question. So if your question is that in this definition, in this yellow box here, right, the notion of equilibrium is with respect to a smoothened version of F, as opposed to just plugging in the function g here. Is that correct?
Yes.
Yeah. So this, I think this seems like a issue because, like for example, in these even simple cases, right, where the function g may be pretty discontinuous. So I'm not sure we can give any guarantee with respect to the g function itself.
But if you made like some additional assumptions, like that it is not discontinuous, but it is Lipschitz, and the gradient can be discontinuous, then
yeah. So that's I think things like that can be done. The only thing I would say is that the function g is not well. It's a function which it's a function which is defined from f. So a condition on g doesn't necessarily translate to any reasonable condition on f. What we are saying is that we have this condition on f. Yes, if we make assumptions on g, which is like an intermediate function which shows up, we can also get bounds. Yeah.
So can you also comment on how big is the dependence on D? Because your slides mentioned polynomial dependence on D, but don't specify.
Oh, I think it's, I don't remember, but I think that's not unreasonable. I mean, it's some small dependence, but it's not linear. If that's, but it's probably quadratic or cubic. I don't remember. Okay. But it's not a practical algorithm, this one. Because it's even quadratic dependence on dimension. Well, I guess so. What is the goal, right? So the goal is that, well, we know optimization has these powerful algorithms, gradient descent, and so on, which are essentially at least explicitly independent of the dimension. Of course, dimension can come in backhanded ways in the Lipschitz constant or other things, but there is still an option for you to run the function, run the algorithm for a small number of iterations and stop. And given that D is large, this this doesn't seem like so some directions that we are we are exploring, and something to think about is I guess this takes us back to this question that was asked before, that this this function f comprises, I mean, it comes from data, right? So it's some sum of some function fi's, where fi in turn is fi in turn is just dependent on a single data point, for instance. And one may ask that, okay, if the data has some interesting geometry, for example, if the data has some interesting geometry, for example, if all the gradients live in some low dimensional space, so maybe the data is a manifold where the tangent space is very small dimensional. So it's in those cases, it is possible to speed these things up. At least in the first order case, we have shown that. In the second order case, I guess we are still a little bit stuck, I would say.
So Nisheeth, there are also two other questions. I think one by Jason, one by Noah. One question from Jason is like, what is the difference of this new notion, this adversarial equilibrium, comparing to the local min-max or the first order Nash equilibrium, which were proven to be like p-pad complete? I think you mentioned this, maybe you can elaborate that a bit more. And then there was another related question by Lord. He was asking like in the convex-concave or other settings, like what is this epsilon greedy adversarial equilibrium comparing to the existing, like comparing to the like normal Nash equilibrium in those like convex concave settings?
Okay, so I'll answer Jason's question first. So in these PPAD hard results, again, I must qualify by saying that I haven't understood, the full implications of these PPAD hard results, but from what I understand, I would say that one of the key difference is that the definition of greedy paths puts no restriction on how far you can go from the current point. Whereas in many of these hardness results or non-existence results, one of the key sources of hardness is the fact that the Y player cannot go too far from where it is currently. But again, I would say that this is just my impression. There are real experts sitting there who can probably make more educated remarks on this. And for the second question of Noha, do you have a result for what epsilon greedy adversarial becomes in the convex concave? So I guess you're asking where the strong convexity doesn't hold, right? Is that correct?
Yes, that's right. Yeah.
Yeah. No, actually, I mean, I don't think we have thought very carefully about this, but I don't think we will. So, okay, so I think the existence results probably will still hold. But in terms of efficiency, things will need to depend on the strong convexity in our setting. So yeah, I think I shouldn't claim that this is a result, but I do remember talking extensively with Oren about this, and it seems like, yeah, we could prove some mathematical result which says that if things are epsilon goes to 0 essentially, and it's in the convex concave case, we will recover the original global min-max solution space. But yeah, I'm happy to talk more offline about this. I don't want to speculate. Yeah.
All right, thanks so much. I don't want to take you more time. I think there was one more question, but I think Manoj will probably contact you offline, and we're going to have 15 minutes coffee break, and we'll reconvene in 15 minutes. And thanks again, Nisheeth, for the very nice talk. Yeah.
Thank you so much.
All right.